Buddy, I hope you're doing well today. As you can see up on the board here, I do have a few announcements to start us off today, and then we'll go ahead look at questions from 10.2, and then we'll start our last lesson of the school year. Can you believe it? The last lesson. It is going to take us a couple days to get through, but still, nonetheless, it's the last lesson. Yay! All right, the first announcement, real fast here, is for the juniors who took the ACTs and chose math as their first final exam exemption pass. I sent emails out this past weekend if you qualified. If you were on the edge of it, because you need to have a 70% to qualify, if you are on the edge of that, I did email you giving you to the end of this week to reach that 70% mark. If you can reach that 70% mark by the end of this week, you can still use your first choice pass in math here for your final exam exemption. If you can't, then it's going to kick down to your second choice. And hopefully you're at a 70% there to be able to use it in your second choice. Prom, real quick, I have a couple people in here who are attending prom on Saturday. An email was sent out, I think probably late last night or early this morning regarding your dinner option. So please fill that out within the next 24 hours so that we know what you're going to eat basically for dinner on Saturday. Isaias, you're the only senior in here that I need pictures for. So if you want to send me pictures for the slideshow, it looks like I couldn't talk you to actually coming into graduation, but I'd still love to include you for all your hard accomplishments over the year. So if you want to be in that slideshow, make sure you just kind of send me pictures for that this week sometime if possible. May 20th is how many days away? Does anybody have a final countdown going on? Aw, thanks, Isaias. That means a lot. All right, anybody got a final countdown? May 20th, how many days? We can do the quick math. Today is May 8th. 12. Yeah, 12 days if you count today. So 12 days until that first deadline of May 20th, which is all your assignments and your tests. May 25th is the second deadline for final exams. And how many days until May 25th? Let's do our 12 plus 5. Yeah, 17. So 17 days until everything is completely wrapped up. Wow, 17 days. And that's including weekends. So that's not even school days. That's actually regular days until that final. Any questions regarding those deadlines before we take a look at the 10.2 assignment? Okay, I'll take the silence as a nope, we're all good to go. Okay, then I did promise we would start by taking a look at 10.02 and answering any questions you have from there. It might just be best to start with the homework assignment and maybe take a look at a question from that homework assignment. We are taking a look at integrals, right? So that is finding kind of the area under the curve. So that's what that 10.02 lesson was all regarding. Does anybody have a particular question, let's see, 1 through 5, that they'd want to take a look at here at the start of class today? So anybody have a particular question, 1 through 5, that you want to maybe run through right now? 1 or 2. Okay, I'm just going to start at the very beginning and we'll choose number 1. Okay, so here is that first question from that 10.2 homework assignment. We want to find the integral from 0 to 9 of the function 2 square root of x. Anybody have any tips for me on what I'm going to maybe do to solve this question? So if you saw this on a test, what might you try to do to solve it? Oh no, it's crickets. We're trying to find the area under the curve, right? So the first thing that comes to my mind is, can we graph that function? If we can graph that function and then maybe partition it from 0 to 9, we can kind of see what we're dealing with. And maybe it's a shape, maybe it's a shape we're familiar with that we can maybe even find the area for. If not, maybe we can break it into our rectangles to try to find the area that way. That's another way. Maybe have your cat walk across the keyboard and whatever they select, hopefully wish for the best when you hit submit. All right, I'm going to go ahead and I opened up GeoGebra. It looks like if you're going to use GeoGebra, it looks like they switched a little bit their formatting. I always do the GeoGebra Classic anytime I need to graph in GeoGebra. Otherwise, if you want to just graph on your own graphing calculator, that's fine as well. So I'm going to do y equals 2 times the square root of x. And I'm going to go ahead and adjust my screen to hopefully get a better view here. And then I'll paste that on the board as well. All right, well, it looks like it's a curved. Yeah, it looks like it's kind of a rainbow shaped graph, right? So if that's kind of a rainbow shaped graph, are we going to have any luck with finding the area of that particular shape? So from 0 to 9, do we have a particular shape that we have the formula of to find that area? No. If it's got a round edge, we probably don't have it unless it's a circle of some sort, which obviously we don't have going on here. All right, so if we have that rounded edge and it's not a nice shape, we have to convert back to our rectangles. So let's draw rectangles in here to partition that off. Find the areas of those rectangles, add them together, and maybe that'll give us a rough estimate of what that area under the curve is going to be. How many rectangles do you want to partition this into? What would make sense? 9. Yep, and I'm going to do the right-hand estimate here. So I'm going to partition this first rectangle right here. What's the area of this first rectangle that I just drew in there? 2, yeah. Let's draw in the second rectangle. What is going to be the area approximately of that second rectangle? I would say probably a 2.8. 3 would be a little bit on the high side because each of these little lines in here is a 0.2. So I think that's going to kind of like a 2. Thank you. I would say probably a 2.8 because each little line in here is a 0.2. So 3 might be a little bit on the high side, but it is an estimate. So you know that it's an overestimate by that fact. So our answer is going to be a little bit higher than what it probably should be originally. When I do the next rectangle, what is that area going to be? Yeah, that looks like a 3.4. Rectangle 4. What's that going to have an area of? 4. Rectangle 5. I'm a little bit high there. I want it to go about right there. Yeah, I would do probably a 4.4. Mine was a little bit on the high end when I tried to go over. How about the next one? $4.9. Okay. I'm going to run out of room. Bummer. Okay. How about that next one? About a 5.3. Two more to go. There's the next one. Is that like a 5.6? Okay. And then the last one. That's a pretty close to a 6. Okay. Let's add all those areas together and see what we get for our grand total. Remember, this is an overestimate. A 38.4 Rachel got. Anybody want to second that? Isaiah's got a 38.43. Depending on the numbers that you used. Okay, so looking at that answer and knowing that's an overestimate because our rectangles went over our curve, what would you come away with as the area under the curve? What would be your best choice? Yeah, probably that 36. Now, how can we determine if 36 is going to be a good representation algebraically? What else could we do to find that a number closer to that value? Yeah, you would take the left-hand estimates, right, or those underestimates. So you would break that into 9 rectangles still, but you go with that left-hand endpoint. So the rectangles would look more like this coming down, right? And then find those areas, add it together, and then average with your overestimate. So you still have this partitioned into 9 rectangles. It's just that they're going to be kept underneath your curve, and then you can average that out. Good. But just for time's sake, we can see that that 36 is probably going to be an average of the overestimate and the underestimate. Okay. Questions with how we did that first one? Any other questions with 10.2 that you wanted to take a look at? So any other questions with that 10.2 lesson? Or is that starting to make a little bit more sense, hopefully? Okay, so we'll look at that sub-interval one. I think that was question 5 or 4, one of those. So I'll look at that. While I'm bringing that up, I just want to mention that the area under the curve here, this is what we call the integral. When you get to calculus, if you're going to take a calculus course, this is also called the antiderivative. So if you hear that term antiderivative being used at all, that is this integral process. There is a way to do this algebraically. Okay, so there is a way to do this algebraically. We will not learn it here in pre-calculus level, but when you take calculus next year, if that's your plan of action, you will learn how to do this algebraically as well. Okay, So the next thing here is Rebecca had a question with those sub-intervals. It says partition the given interval into the indicated number of sub-intervals. So first of all, the interval we're looking at is from 0 to 2. So if I were to draw out a number line from 0 to 2, so starting at 0, ending at 2, we need to partition this into 8 sub-intervals. All right, so what am I actually going to do to figure out how wide each sub-interval is going to be? So let's say I wanted to put 8 rectangles between those two numbers. Yeah, you would take your 2 and divide it, because 2 is the distance between there, right? 0 to 2, that's 2 spaces. You would go ahead and divide that by how many partitions you need. So that means each rectangle will have a width of 1/4. That's exactly correct. So when it's asking for this, I know we're counting by 1/4. I'll go ahead and add these numbers in. And just to verify, you should have 8 spaces here, right? So the first sub-interval is happening between 0 and 1/4. The second sub-interval is happening from 1/4 to 1/2, then 1/2 to 3/4, then 3/4 to 1, 1 to 1/4, 1 and 1/4, 1 and 1/4 to 1 1/2, 1 1/2 to 1 3/4, and lastly 1 3/4 to 2. Sorry, I was using random colors there. So there you can see those are the 8 intervals that you would partition that into. So you'd have to actually list all of these out. So 0 to 1/4, 1/4 to 1/2, and so forth. Okay. Questions with how we figured out how to partition up that interval from 0 to 2? Awesome, fantastic. Sometimes we overthink some of this calculus stuff because we're like, it can't just be that simple, because this is kind of what you learned back in maybe even middle school, is how to split things into equal parts, right? That's exactly what we're just doing here as well. So sometimes we have that generalization to kind of overthink things, but it is just that simple of splitting it into the 8 equal pieces. Yeah, good. Any other questions regarding lesson 10.2 at all? So from what I saw from the assignments coming in, for those of you who did submit the assignment, things looked pretty good. There may have been just 1 or 2 mistakes along the way, but nothing that was catching my eye and like, oh my gosh, we have to talk about this and address it again. So most of it went pretty well. Okay, then that brings us to the last lesson. Woohoo! My husband sits in the background, and every time I say woohoo, he's like, oh, she said it again. So he's probably going, oh man. It's like one of those things when you're giving a speech and you find yourself saying a lot, like I think I say woohoo a lot as a filler. So he catches me on it all the time. He's like, you did it again. You did it again. Okay, so back to our limits. So these limits help us find what our graph is approaching as we get closer to a certain value, right? So we've seen these before. We found derivatives using our limit process. When we did our derivatives, we let the limit go to 0, right? Usually it was h going to 0, and we would substitute in 0 for h at the very end after we simplified things completely. We can do that same kind of process and finding the actual limit just by looking at 3 different techniques. So the first technique you can do to find a limit is graph the function and see what you're actually approaching. All right, so look at that graph. What is the graph getting closer to as x goes to 3? That type of deal. We might actually be asked for the limit as x goes to infinity or negative infinity. Remember, that's just when your x values are getting extremely large. What is your graph doing? Is it getting closer to a certain number? Is it still increasing without bound? Is it decreasing without bound? So in this last lesson, we'll take a look at what happens when our limits approach infinity or negative infinity. We can also have our limits equaling infinity or negative infinity as well. So this happens with those exponential functions or our parabolas or basically anything that continues in an upward or downward direction and doesn't level out at some point. Okay, so a couple of things that we're actually going to explore further here in this last lesson. All right, to find a limit, I said that we could look at it graphically. We can also solve it numerically by taking a look at the table of values. We do not do this middle option very often. Okay, this is not one of my favorites. I mean, you can definitely do that. It is beneficial at certain times, but I think that graphical representation is going to be a little bit more practical than maybe the graph or the table of that. But if you're having a hard time visualizing what that limit is as it gets close to a certain number, the table can help you figure that out. Okay, so if you have a hard time with the graphical approach, the table can be beneficial. The last approach is algebraically, and I will be focusing on this one the most. So graphing and algebraic are going to be the 2 methods that we focus on to help us find a limit. Okay, so they do give us an example here to start us off. It says find the limit of this function right here as x goes to 1. So what we have to do is I would graph this function right here. So I would graph that, which they have below for us. It looks almost like a parabola shape. And then I would see what is happening to my graph as x goes to 1. So from the left-hand side, my graph is going to what value? So here is the left-hand approach. What is that getting closer to? And the right-hand approach is the same thing. What is that value getting closer to on both parts of my graph? So as I zoom in to that x equaling 1, what is my graph approaching? So what value is that? Well, I would come off to the left here. Yeah, it looks like it's approaching a 3, just about, right? So if I were to look at x equaling 1 and zoom over, that's probably at that 3 mark on the y-axis. So we would say that the limit as x goes to 1 of this function equals 3. You can view that in the graph as well, or that table as well. So if I went to the table feature of it, notice as it goes to 1, there is an error spot at that 1, right? So looking at each side of it, below it, it is getting closer to the number 3, and above it, it is getting closer to the number 3 as well. So that's why we would say it approaches 3 there. Algebraically, we want to try to simplify this as much as possible, because if I use substitution right off the bat and I plug 1 in for x, I would get a 1 cubed minus 1 over 1 minus 1, and the numerator doesn't really bother me as much as the denominator does, because I get 0 in the denominator there. So I have to try to simplify that before I can substitute 1 in. So I would factor the numerator. That is a difference of cubes pattern right there. So it does break down into this being factored. And then I notice I can cancel out the x minus 1, which is really good, because if I can cancel that out, I then am going to essentially eliminate that 0 that I had in the denominator. That should take care of all of my issues. Once that was simplified, now I can use that direct substitution. So substituting that 1 in for x, because that's what it's approaching, and simplifying from there, I would get 1 plus 1 plus 1, which gives us a total of 3. So the first and the last options are what we're going to kind of favor when we look for our limits. Okay, any questions with that first example before we look at some other ones? Okay, before I get too far, I just want to show you the properties of our limits. None of these should really surprise us because we've seen them with other functions before. So like with our logarithms and exponents and, well, not maybe exponents, but our logarithms, we've seen some of these rules before. So with the sum rule, if you have two functions here, you can find the limit of each function separately and then add them together to find that total end limit. Okay. Same thing with the subtraction. You can kind of separate the two terms in that subtraction, find the limits individually, and then subtract those. Excuse me. I'm sorry. And then the product rule and the quotient rule is just what you would think as well. So multiplying the limits individually, dividing them individually, multiplying through by a constant. You can take that out, find the limit first, and then multiply it through by that constant again. Same thing with your powers and your roots as well. So roots, remember, are those fractional exponents. So nothing really spectacular here. We'll see some examples where we use some of these properties, but they're pretty straightforward at this point. It's what we would expect us to be able to do with these limits. Okay, so use the limit properties and the fact that the limit as x goes to 0 of sine of x over x does equal 1. So we're going to use this fact right here and my properties that we had listed on that previous slide to help us find these more complicated limits. Alright, so any ideas what we can maybe do to find the limit of this first example here in part A? So if you saw this function, what might you try to do to simplify the process with finding the limit? Yeah, kind of break up the function, right? So you'd have the limit as x goes to 0 of x over x plus the limit as x goes to 0 of sine of x over x. All right, x over x, what does that simplify to? So yeah, it's really tempting to put in a 0 over 0, but that just simplifies to a 1. That's really just a constant of 1 there. So that's what the limit as x goes to 0 of x over x is approaching. It's approaching the number 1 because that's what this simplifies to. And then now we can use that fact that the limit as x goes to 0 of sine of x over x equals 1 from up above. So the total limit of this function in part A is going to be 1 plus 1, which is a 2. So the limit of that nasty looking function that we started with is going to be 2 because we found that by breaking it into two smaller pieces that we could easily handle. That's going to be kind of our go-to strategy with some of these more complicated setups. All right, part B. So part B is relying on you remembering some information from earlier in the school year. What tactic do you think we can take with part B? So substitution right off the bat would not work because you get 0 squared in the denominator. And we know we can't divide by 0. So there's got to be a way we can split this up of some sort. Yes, so Tommy says that numerator is a Pythagorean identity, right? So we can replace this 1 minus cosine squared with a sine squared x. That's a very good start. All right, it's not the only thing that we need to do though, because if I use substitution at this point, I still get 0 in the denominator. So what might you try to do once you replace that numerator with your sine squared x? We don't necessarily have to factor, although I think you might be thinking along the right lines. Yeah, we're going to split it, but not using addition in the middle anymore. We're going to use multiplication in the middle. Yeah, because technically we would need to multiply those two things. So we're going to do the sine of x over x, and we're going to multiply that by the same thing. If I split that up like this and I do that multiplication, that would bring me back to the sine squared x over x squared. All right, I know what each of these limits is going to approach. What is the limit as x goes to 0 of sine x over x? Just a 1. Yeah, so each of those is a 1, but now I have that multiplication sign that connects them. So what will be my limit overall? Yeah, a 1. Very good. All right, the last one. Gotta love these radicals here. So any ideas for me on the last one? I've got two separate radicals. Do they have the same index? So maybe we should start there. Do those radicals have the same index? They do. They both have an index of 3. So if they both have the same index of 3, I can keep that index of 3, and I can actually divide what's underneath them. So sine of x over x. Now that we see that, maybe some things are jumping out to you. Any idea what we can do now? Yeah, so essentially what we have to do before we substitute 1 in for that sine of x over x is I have to move the limit underneath. So that root rule right here says if the limit's on the outside of that radical, you can move it underneath and simplify that first and then take the radical of that value. So technically we have to do our root rule here, and I'm going to move the limit underneath that radical sign. Now I can go ahead and replace that with the 1. Notice that it's still being kept underneath that radical sign though. What is the cubed root of 1? Yep, so that is going to simplify down to just a 1. Great. Any questions with that at all? And seeing kind of some of those properties used and some strategies there to simplify those A, B, and C examples. Okay, if you can't figure out how to simplify something, you can try substitution at any step. But if you get 0 in the denominator when you use your substitution, you know that you need to try to backtrack and separate things or find maybe the limit separately somehow or rewrite it like we did in those previous examples. But sometimes substitution will work right off the bat. So let's just check out what is cosine squared of x if x is going to approach 0. So sometimes I just use direct substitution to see what we get in the denominator. If it's something other than 0, we might luck out and be able to use direct substitution right off the bat. So what is cosine squared of 0 as x goes to 0? And technically we can do that as cosine 0 squared. We can move that exponent out. Tommy gets an error. Let's see what I get. Oh, I get something different. I wonder if it matters the mode I'm in. Nope, it doesn't. So if we try moving the squared on the outside here, I think that's going to make a difference because Rachel then got a 1 and Isaias got a 1 as well. So we got something other than 0 in that denominator. That's looking pretty good. We might be able to use direct substitution right off the bat to find this limit. So I'm going to go ahead and now I'm going to use direct substitution in that numerator as well. What is e to the 0 power? You don't need a calculator for this. Remember your exponent rules. What is e to the 0 power? A 1. Anything to the 0 power is a 1. All right, you probably will need your calculator for the tangent though. What is tangent of 0? Or you can be thinking back to your unit circle as well. Yeah, you do get 0 there. So using direct substitution, we get 1 over 1, which just simplifies down to a final 1 for that overall limit. So we luck out once in a while, and we can use direct substitution right off the bat to find those limits. How about the second one? Let's check it out. Let's use direct substitution right off the bat again and see if it's going to work out for finding our overall limit. Now, in that denominator, because I generally would start with the denominator, because if I get 0 there, I know I'm going to have to backtrack and try to simplify some other way. So generally, I start with the denominator to see what we get there, and then I find out what that numerator is going to be. So how exactly can I figure out what that denominator is going to simplify to? We have to go back to our logarithm days. You have to use the change of base formula. Yep, in order to do that on the calculator, you have to do that change of base formula. So log of 16 divided by log of 2 is going to simplify to a 4. Okay. The numerator, square root of 16, I think we all know that is a 4 as well. Because we did not get 0 in the denominator, let's go ahead and simplify here. What is 4 over 4? A 1. Okay. These are my favorite type of limits here, is when we can use kind of the direct substitution right off the bat. I know a lot of our examples come away with the limit as 1, but I promise you that you can get other numbers there other than 1. It does seem to be a common answer though for some of our limits. But I promise you it can be any other number. It can be a positive value, it can be a negative value, it can be a decimal. Right? If only all of our limits would be 1. It would make our lives a lot easier. Okay, I'm trying to see where, I think we're going to stop right here. I know it's a little bit early, but we can afford to stop right here and pick up where we left off in Thursday's class. So that's what we're going to do. We're going to stop right here by the one-sided and two-sided limits. So if I forget where to pick up on Thursday's class, remind me, one-sided and two-sided limits. Okay? That's where we're going to pick up off. So we've got a couple more topics we still need to cover, but we definitely talked about our properties for limits and that direct substitution process. So a couple more things to cover. If you want to take a look at the assignment, you can, but I don't think you can get very far in it. You might be able to answer a couple questions, but don't submit it or anything because we still have some more topics to discuss on Thursday. All right, any questions with what we covered here this morning? Okay, if anything, finish that 10.2 lesson between now and Thursday. So we saw a couple more examples from that homework with 10.2. Maybe work on corrections or finish that up. And then we'll pick up with those one and two-sided limits come Thursday morning. All right, Isaiah, stick around because I saw you had a question, so we'll get that addressed. Everybody else is free to leave. Have a great rest of your Tuesday, and I'll see you Thursday morning again.